Check it out now, y'all.
Nano Hub U, online instruction.
Welcome to tutorial 2.1, and as you know, in the lectures we had talked about how you can translate a given energy momentum relation into a density of states. And I guess this homework is designed to give you some practice with that. And what I'd asked you to do is I gave you 3 different energy momentum relations. See, and the ones were V0P, that's a linear relation, as I said, a very important material that's of lot of interest these days. Graphene has that linear energy momentum relation. Then there is the usual EC plus h bar square, or rather p square over 2m. That's the usual parabolic one that you see. And I gave you a more general one, which is like E equals square root of EC square plus V0 square P square. Now, what we'll do in this tutorial is, we'll do this one. And the reason is that, you see, these two are kind of like special cases of that. That if you have done that, you can actually deduce what it should be for these out of that. Like one of them you can see easily, that if you wanted the linear result, all you'd have to do is put EC equals 0. Because then, you see, equal to this. If EC is equal to 0, then basically what you get is E equals V0P. Done. Now, what's not so easy to see is the parabolic one. That what I claim is that if you make EC sufficiently large, so if V0P over EC is small, then this is essentially just like a parabolic relation. And the way you can see that is, write it the following way. Pull this EC out, so that inside you can write it as 1 plus V0 square P square over EC square. And then what we argue is that if this is a small quantity, then you can use this binomial expansion, which is square root of 1 plus x is 1 plus half x. So you could then write this as EC times 1 plus V0 square P square over 2 EC square. So this is square root of 1 plus x. X is small, so you can write it as 1 plus half of x. Okay. And so what you get then is, you see, E is equal to EC. So if you multiply it out, EC, and then plus, you get so you'll notice the result is E is equal to EC plus something times P square. So you have effectively got a parabolic relation, and you could identify this quantity, EC over V0 square, as your mass. So that's like the mass. Then it looks like P square over 2m. Okay. Anyway, so bottom line is, what I'm saying is, what we'll do is go ahead and find the density of states for this one. And the other two are kind of like special cases for that. So if you go to these limits, you'll get what you can deduce the answers. Or, of course, you could just start and do it directly from here also. That's fine. But in this tutorial, I'll just do that one. Okay. So this is E of P. And what we want is the density of states. And if you remember, the overall procedure is first step, we need to write n of p. That is, how many states do we have up to a certain maximum value of the momentum, p. And that is where, as you know, we had these expressions we derived in the lectures for 1D, 2D, and 3D. And what I asked you to do this was for 2D. And for 2D, the expression looks like p over h squared. Because in general, it's always p over h raised to the power of the number of dimensions. And then there is this constant multiplying it, pi times the area, width and length. So that is the expression for n of p. Now the next step is combine those two things to get an expression for n of e. And if you do that, then what you'd have is the total number of states up to a given value of energy. And if you take the derivative of that, that's how you'd get the density of states. So to get the n as a function of e, then what we need to do is replace the p here from here in terms of e. So the way it would work is, I need to turn this one around. So this is e as a function of p. I need to turn it around so I can express the p as a function of e. And then I can replace this p with it. So I can write e squared is equal to ec squared plus v0 squared p squared. So what that tells me is p squared is equal to that's it. So what I can do is take this p square from here and replace it with what I have from there. So what I'll get is so that's it. So that's the expression for this total number of states up to a given energy, E. Now, if I want the density of states, then what I need to do is take the derivative of that. So let's do that. What you'd get is, yes, I can write it here. See, I'm taking the derivative with respect to energy, and only this term involves energy. That's just a constant. So when I take the derivative, it's just 2e. That's it. So I get 2e divided by h square v0 square. So this is then the density of states. Yeah. So if you actually were to plot it, it would have looked something like this. That, you know, E versus P, so this is energy versus P, and for P equals 0, the energy is EC, and then from there it goes up. And this density of states is proportional to the value of the energy. So if you looked at the density of states, then if I'm plotting the density of states, it would look something like, of course, out down here it is 0 if the energy is less than EC. It is all starting from here. So from here it then goes up. According to this expression. So that's the density of states. Now what I also asked you to check is that a relationship that we had derived in the lectures, which is supposed to be independent of the energy momentum relation. And that is that density of states,